Affective behavior analysis aims to develop emotionally intelligent technology that can recognize and respond to human emotions. The 7th Affective Behavior Analysis competition establishes 2 tracks: the Multitask Learning (MTL) Challenge and the Compound Expression (CE) Challenge, based on the AF-Wild2 and CEXPRDB datasets. To attain high-quality facial features, a Masked-Auto Encoder is trained in a self-supervised manner. A temporal convergence module is devised to capture temporal information between video frames, exploring the impact of window size and sequence length on each subtask. Subtask joint training and feature fusion from individual tasks facilitate the joint optimization of various subtasks, improving task performance. Curriculum learning is utilized to transition the model from recognizing single expressions to recognizing compound expressions, thereby improving the accuracy of compound expression recognition. The MTL challenge involves 3 subtasks: action unit, O, prediction, expression recognition, and valence-arousal, VA, estimation. To improve the final performance of the model, the focus is on learning general and powerful features, achieving knowledge transfer between tasks, and fully utilizing spatio-temporal features in the data. A feature extractor is trained in a self-supervised manner, integrating almost all existing facial datasets. A feature fusion module is employed to integrate features extracted by pre-trained models with the features of the current training model. For the CE challenge, the goal is to achieve compound expression recognition in videos with limited amounts and unknown labels. The challenges are to utilize existing data to train models effectively and validate their performance on compound expressions with labeled data. To achieve this, existing expression recognition datasets are utilized to train the model, followed by the employment of cut mix and mix-up techniques to generate compound expressions. Curriculum learning is introduced to transition from single expression recognition tasks to compound expression recognition, enhancing the model's generalization ability and leading to better performance on unseen data. Extensive experiments demonstrate the superiority of the proposed methods, showcasing the effectiveness of the designed features, temporal convergence module, feature fusion, and curriculum learning in improving the accuracy of compound expression recognition. The research focuses on affective behavior analysis, particularly in the areas of multitask learning, MTL, and compound expression recognition, CER. In MTL, recent advancements have demonstrated the effectiveness of jointly learning tasks like emotion recognition, action unit, O, detection, and valence, VA, estimation. This approach enhances performance by capturing shared emotional cues. For CER, methods utilizing convolutional neural networks, CNNs, and recurrent neural networks, RNNs, have shown significant improvements in accuracy. The proposed framework for MTL involves feature fusion from other task models and the use of a temporal convergence module to capture dynamic expression information. For CER, the approach starts with a multi-class model trained on single expression labels, gradually increasing the proportion of compound expression data. The feature extractor employed is a Masked-Auto Encoder, which is trained in a self-supervised manner on a large-scale facial dataset. The model is fine-tuned on AffectNet and AF-Wild data for better adaptation to affective behavior analysis. Here is the combined summary of pages 5 and 6. The authors propose a progressive learning approach for affective behavior analysis via multitask learning, MTL, and compound expression recognition. In the MTL track, they transition from single-task learning to multitask joint learning, using a feature extractor with multiple heads for different tasks. The authors explore the impact of joint training and feature fusion on model performance. Specifically, they extract output features from each task after individual training and introduce a feature fusion module to combine features from different tasks. This fusion module consists of 2 linear layers, an activation layer, and a dropout layer. The authors demonstrate the promotion effect of feature fusion on different tasks in the experimental section. To capture dynamic expression changes over time, the authors construct a temporal convergence module, consisting of 2 LSTM layers and a leaky ReLU activation function. This module aggregates information across each time series, resulting in more comprehensive expression features. However, not all tasks employ the temporal convergence module, and its performance varies significantly with different window sizes and sequence lengths. In compound expression recognition, the authors adopt a progressive training strategy, starting with single expression recognition tasks and then introducing compound expression recognition. This approach increases the difficulty of tasks, allowing the model to adapt to identifying blended or compound expressions. To enhance dataset diversity, the authors utilize cut mix and mix-up data augmentation techniques to generate compound expressions. The authors fine-tune the model on the RAFDB and FuxE-EXPR datasets, using cutout data augmentation and basic data augmentation techniques. They progressively introduce more complex compound expressions to train the model, dividing the training stage into 4 substages with increasing proportions of compound expressions. During inference, the authors constrain the final results into officially provided compound expression categories, summing classification probabilities of individual expression categories involved in the compound expressions. This research paper presents a comprehensive framework for effective behavior analysis via progressive learning. The authors propose a multitask learning strategy that jointly trains 3 subtasks: action unit, O, detection, expression recognition, EXPR, and valence-arousal, VA, estimation. The training objectives for each subtask are defined as follows. For O detection, the authors utilize binary cross-entropy, BCE, loss. For EXPR, they employ cross-entropy, CE, loss. And for VA estimation, they leverage the consistency correlation coefficient, CCC, as the model optimization function. The joint learning strategy combines these objectives using weighted sums, where the weights are hyperparameters to be tuned. For compound expression recognition, the authors adopt a binary cross-entropy multilabel loss function. The overall training objective is a weighted sum of the individual objectives, where the weights are set to 0 if a subtask is not involved in joint training. The authors conduct experiments on several datasets, including AffWild, CEXPRDB, AffectNet, Cache Webface, Celeba, IMDBWIKI, Webface 260M, and FuxE-EXPR. They filter out invalid data and pre-process the datasets to ensure consistency. The datasets are categorized into various expression types, including neutral, anger, disgust, fear, happiness, sadness, surprise, and others. The authors also utilize additional datasets, such as BP4D, RAFDB, and AffectNet, to supplement the official datasets and address limited coverage of certain O categories. They retain only the 6 basic emotions for the datasets to obtain stable performance. The experimental setup and dataset preprocessing are crucial for the proposed framework, and the authors provide detailed information on the datasets and their characteristics. Here is a combined summary of pages 9 and 10. The authors propose a multimodal effective behavior analysis framework, which involves the estimation of valence, arousal, and expression categories, as well as action unit detection. The performance of the framework is evaluated using 2 metrics. One for the multimodal task learning, MTL, track and another for the cross-entropy, CE, track. The MTL metric combines the mean concordance correlation coefficient, CCC, for valence and arousal, the average F1 score across all 8 expression categories, and the average F1 score across all 12 action units. The CE metric is measured by the average F1 score across all 7 categories. The authors implement their approach using a progressive learning strategy, where all training images are resized to 224 × 224 pixels. The mean absolute error, MAE, pertains to 8 NVIDIA A30 GPUs with a batch size of 4096. Experimental results on the validation dataset show that the proposed approach significantly outperforms the baseline model in the MTL track, achieving scores of 0.6533, 0.5030, and 0.6351 for average CCC, FEXPER, and FOS, respectively. For the CE task, the authors achieve an FS score of 0.6856. The authors also investigate the impact of the feature fusion module on each task model. Experimental results show that combining features from other task models via the feature fusion module does not universally enhance the performance of all task models. The degree of performance improvement varies significantly depending on the fused features. For instance, for the O task model, the best performance is achieved without using the feature fusion module, whereas for the EXPR task model, fusing features from the O task model improves performance by 1.4%. Furthermore, the authors evaluate the impact of introducing the temporal convergence module on different tasks. Results show that the module achieves significant improvements in the valence and arousal estimation models, with CCC values improving by 2.36% and 3.45%, respectively, compared to training on single frames. However, the performance of O and EXPR task models is not enhanced. The research paper discusses the analysis of affective behavior through progressive learning, focusing on the impact of the temporal convergence module and the joint training strategy. It presents the performance of models on various tasks, including O, EXPR, V, and A, under different sequence lengths and window sizes. The results indicate that adjusting the sequence length has a more considerable effect on performance, with the best results achieved for valence estimation with a sequence length of 20 and for arousal prediction with a sequence length of 30. The joint training strategy improves the performance of all task models, especially when combined with the temporal convergence module and feature fusion module. The paper also explores the impact of curriculum learning, presenting the best performance achieved under specific epoch distributions and compound data proportion distributions. Here is the combined summary of pages 13 and 14 of the research paper. The authors present their methods for the 7th Affective Behavior Analysis, ABA, Multitask Learning Challenge and the Compound Expression Recognition Task. They train a robust facial feature extractor on a large-scale facial dataset and fine-tune it on downstream task datasets to obtain high-quality facial expression features. For the multitask learning task, they devise a feature fusion model to fuse features extracted from other affective analysis tasks, improving model performance for EXPR, valence, and arousal estimation models. Additionally, they introduce a temporal convergence model to capture expression dynamic changes over sequence frames, enhancing model performance for valence and arousal estimation models. For the compound expression recognition task, the authors employ a curriculum learning strategy, allowing the model to effectively transfer learned features and adapt to the more complex task of identifying blended or compound expressions. They also utilize different data augmentation techniques to generate new compound expressions, maximizing the utility of available data. Experimental results show that incorporating mix-up and cut-mix data augmentation methods enhances model performance, with the highest F1 score value achieved when both methods are used simultaneously. The authors also analyze the effect of dividing the training process into multiple stages, finding that model performance does not always improve with an increasing number of training stages. They demonstrate that adjusting the distribution of compound data to be more even across stages can lead to decreased performance. The paper provides a comprehensive review of the state-of-the-art in affective behavior analysis, citing various studies on facial expression recognition, multitask learning, and affective computing. The authors highlight the importance of developing robust and efficient methods for analyzing affective behavior, with potential applications in human-robot interaction, healthcare, and other fields. In the realm of affective behavior analysis, progressive learning has emerged as a pivotal approach for understanding human emotions and expressions. This paper provides an extensive overview of recent advancements in this field, focusing on deep affect prediction in the wild, valence-arousal recognition, and compound expression analysis. The AffWild database and challenge, introduced by Collias et al., has significantly contributed to the development of deep architectures for affect prediction. These models leverage large datasets and advanced neural networks to predict emotions from facial expressions, speech, and physiological signals. Moreover, the AffWild 2 database extends this concept further by incorporating multitask learning and ArXiv for enhanced performance. A unified framework for affect analysis in the wild, proposed by Collias and Zafariu, integrates valence-arousal, expressions, action units, and a unified framework. This comprehensive approach enables researchers to analyze affective behavior more effectively in various contexts. The ABAW competition series, initiated by Collias et al., aims to foster innovation in affective behavior analysis. The 7th ABAW competition emphasizes multitask learning and compound expression recognition, encouraging participants to develop novel methodologies that can handle complex emotional states. Several studies have explored the role of audio-visual fusion for emotion recognition. For instance, Praveen et al. Utilized joint cross-attention to combine audio and visual cues for improved valence-arousal estimation. Similarly, Liu et al. Demonstrated the effectiveness of bootstrapping audio-visual segmentation by integrating foundation knowledge. In addition, transformer-based models have shown promising results in video frame-level prediction for affective behavior analysis. Nguyen et al. Employed a transformer-based approach to leverage long-range dependencies in video sequences. Overall, this paper highlights the rapid progress made in affective behavior analysis via progressive learning. By leveraging deep learning techniques, large datasets, and innovative methodologies, researchers can develop more accurate and robust systems for understanding human emotions and expressions. The research focuses on affective behavior analysis, particularly in facial affective analysis. It discusses various methods for facial expression recognition, including super resolution, hallucination, and joint frontalization of unaligned tiny faces. The study also surveys sentiment analysis in social media and multimodal sentiment recognition. Additionally, it explores multitask learning frameworks for emotion recognition and multimodal facial affective analysis. The methodologies involve deep learning techniques, including convolutional neural networks, autoencoders, and transformers. The research highlights several key papers and their contributions to the field, emphasizing the importance of integrating multimodal knowledge for accurate affective behavior analysis.